It's 8 pm on a Friday, and half of Mumbai just opened Swiggy at the same time. You tap order, so does a lakh of other people, right now, simultaneously. And somewhere in a data center, one poor server starts sweating, the app slows down, some orders fail, and every engineer on call gets a message. But here's the thing, it's slow or it's down doesn't actually tell you what broke. Because slowness has three completely different causes, and you need to know which one you're dealing with. When an engineer says the system's struggling, they're really asking one of three questions. How long does a single order take? End to end. How many orders can we handle per second? And how much data can we actually move at once? Three different questions, three different problems, three different fixes. And mixing them up is how you spend a weekend firefighting the wrong thing. Let's start with the first one, latency, which just means how long one single request takes. You tap order on your phone. That's the client, the thing making the request. The request travels to Swiggy's server, maybe 12 milliseconds over the network. The server needs to check the restaurant, fetch your address, calculate the delivery fee. So it hits the database, and that query takes around 40 milliseconds. Then the answer comes back. Another 8 milliseconds to process, 5 milliseconds back to your phone. Total 65 milliseconds, that's latency. The time for one round trip door to door when latency is low, the app feels instant. When it's high, you sit there watching a spinner. So what makes latency go up? There are three main culprits, and they show up in almost every slowness investigation. First, physical distance. If you're ordering from Leh and the server is in Mumbai, the signal is literally traveling hundreds of kilometers. That adds latency you cannot code your way out of. Second, server processing. If your order triggers 10 different calculations, discount codes, surge pricing, restaurant availability, each one adds time. And third, almost always the sneaky one, the database. A query without the right index doesn't find one row. It scans every single row in the table. Distance is physics, processing is code, but the database is usually where the real time goes. Now latency answers how long does one request take? But that's only half the picture. The other question is how many requests can be handled at the same time? That's throughput. Imagine a pipe. One order travels through it per second. 1 QPS, queries per second, which is the unit engineers use. Now imagine we make the pipe wider. Or better, add more pipes side by side. Now 100 orders a second can flow through. And a well-engineered system at scale might handle 10,000 QPs or more. Throughput isn't about making one request faster. It's about how many requests you can serve simultaneously before the system starts refusing or slowing down. Here's the analogy that makes this stick, and we'll keep coming back to it all season. Imagine a kitchen with one cook. That cook can make one dish at a time. One order per minute, let's say. That's your throughput. 1 QPS. Now you hire 4 cooks. Each one still takes the same amount of time per dish. The latency per order hasn't changed. But now you're serving 4 orders simultaneously. Throughput just quadrupled. But the kitchen itself, the physical space, the number of burners, the gas supply, that's bandwidth. Each cook's speed is latency. The number of cooks is throughput. The kitchen size is bandwidth. So, bandwidth, the width of the pipe. If you're on a standard Joe connection, you've got maybe 25 megabits per second of bandwidth. A text-based order request, a few kilobytes, flies through with room to spare. But a 4K YouTube stream needs around 15 megabits per second just for one video, and your connection is 25. So if 2 people in your house are streaming 4K, you've hit the ceiling. Scale that up, 32 million people streaming the IPL final simultaneously, each needing 15 megabits. That's 480 terabits per second of bandwidth that has to exist somewhere in the world. Here's where a lot of people trip up. Latency and throughput are independent. You can have high throughput and high latency at the same time. They're not opposites. Think about the Western Express Highway on a Friday at 8 pm. Thousands of cars are on the road. That's high throughput, but each car is stuck in traffic. High latency. Many requests being handled, but each one taking forever. That's not a contradiction. That's congestion. Now, picture the same highway at 3 am. One car, no traffic, doing 120. Low latency, you're flying, but only one car is moving. Very low throughput. This is exactly what IRCTC looks like at 10 am on Tatkal booking day. Thousands of requests hammering the server simultaneously. Each one taking 20 seconds. High load, terrible latency. Understanding which one is your problem completely changes what you do next. Okay, so how do engineers actually measure this stuff in the real world? 3 numbers come up constantly. And once you know them, you'll spot them everywhere. First, QPS, queries per second. How many requests is the system handling right now? 12,000 QPS means 12,000 orders every second. That's the throughput number, the live pulse of the system. Second, P50 latency, the 50th percentile. Half your users got a response faster than this, half slower. If P50 is 45 milliseconds, the typical experience is pretty snappy. Third, and this is the one engineers actually care about most, P99 latency. 1% of requests took this long or longer. If P99 is 820 milliseconds, that's 1 in every 100 users sitting there for nearly a second. On a system doing 12,000 QPs, that's 120 people every single second having a bad experience. Here's why P99 matters more than the average, and why the average is actually a bit of a liar. Imagine you plot every request's response time as a curve. Most requests are fast. That's the big hump in the middle. The average or min sits somewhere in that hump. 52 milliseconds. Looks great, right? But there's a long tail to the right, where a small fraction of requests took much longer. P99 is out here at 820 milliseconds. That tail isn't a statistical artifact. Those are real users, real people. And they're the ones who leave the 1-star reviews. If you only watch the average, the tail is completely invisible to you. P99 is how you see it. Let's go back to our 8 pm Swiggy rush, because now you have the vocabulary to understand exactly what's happening. Here's the traffic pattern over the day. Flat in the morning, picking up at lunch, then at 8 pm it spikes hard. The system's throughput ceiling, the maximum it can handle, is 5000 QPs. That's a line. The spike crosses it. When demand exceeds throughput, requests don't disappear. They wait, a queue forms, orders are stacking up, and watch what happens to P99 latency as that queue grows. It goes from a healthy 45 milliseconds all the way to over 8 seconds. The kitchen didn't get slower. There are just more orders than it can cook. Let me give you a real-world example of bandwidth at scale, because the numbers are genuinely wild. The IPL final on Hotstar in 2023, 32 million concurrent streams at its peak. Each stream needs roughly 4 megabits per second of bandwidth. That's 128 terabits per second of total bandwidth that has to flow from servers to every viewer's screen simultaneously. You cannot serve that from one building in Mumbai. This is why Hotstar pre-positions the video in CDN nodes scattered across India. Each viewer pulls the stream from a nearby node. Bandwidth is why the CDN exists. Now, here's the engineer's decision. The trade-off at the heart of this episode. Latency and throughput are often in tension, and you frequently have to choose which one you're optimizing for. Take a UPI payment. When you tap, pay and send 500 rupees to someone. That money needs to move. Right now, you need a response in under 500 milliseconds, or the UX feels broken and the user panics. This is a latency-first system. To guarantee that latency, you actually end up handling fewer requests at once. You trade some throughput to protect the latency. Now contrast that with Swiggy's internal analytics pipeline. The system can collect 10 million events through the day, batch them up, and process the whole lot every 10 minutes. That's a throughput first design. You get massive efficiency by processing in batches, and the latency is perfectly acceptable because nobody needs the answer instantly. The same data, the same infrastructure, and completely different priorities depending on what the system is actually for. So, here's what you now have: three numbers that together tell you almost everything about a system's health. Latency: how long one request takes end to end, measured in milliseconds, tracked at E50 and P99. Throughput: how many requests the system handles per second, measured in copies and bandwidth. The physical ceiling on how much data can flow at once, measured in megabits or terabits per second. In the next episode, we go one level deeper into the full vocabulary engineers use to talk about scale. What does 4 nines of availability actually mean? Why does 99.9% uptime still leave you with 9 hours of downtime every year? That's episode 4, and it builds directly on everything you just learned.